Well, hi everyone, and welcome to week 14, the last week and lesson packet of the year. This week we're going over glacial landforms and landscapes and coastal processes and landforms. Do be advised that there's material in the coastal lesson that is not covered in the book, but yet covered by the quiz. So please pay attention. It's not difficult. It has to do with the engineering structures that are set in the ocean and on the beach, but definitely well worth going over, even though your book doesn't. So we'll begin, of course, with part one, landscapes of glacial origin. This image here is it's called Perito Moreno Glacier in the hook of South America. So this is in Argentina. It's one of those interesting landscapes that is immediately next to a forest on either side of it and in front of it. This is, of course, a outlet glacier, meaning it empties into the ocean. It isn't an ice sheet, and we'll go over those coming up. So when you look at a glacier like this one here, you can see that the snout, or the front end of it, is dirty. It's full of rock, it's full of silt and sand and pebbles. There's a lot of debris. There are braided streams that begin on its edge. And there's a lot of material. So there's a braided stream because there's variable water. In winter, it's frozen, so there's no meltwater. In summer, it suddenly bulges with water. And there's a lot of debris that's carried out. So you see the braided pattern right there in front of it. You can see all the material that's been scoured out, and there's like little tributary glaciers feeding it. Now, here you see this, we'll talk about the idea of the firn, F-I-R-N line. This is where you go from melting and ablation to the zone of deposition. Notice how bright and white and dry and cold the glacier is up here compared to down lower into the river valley, basically, as it were. Here's another image, a little bit up close to the end of the glacier before it melts completely. Notice how much rock. Ice is an exceptionally good carve mechanism. It really tears through rock. It may do so slowly, but it does so very effectively. And it carries a lot of material with it. So by the time that ice is sort of at its last stage, it's very crumbly, very dirty, and full of material. Think about the snowplow when it dumps all that snow at the end of the mall parking lot. You know what I'm talking about, right? All that junk that it carries with it, that's basically what the glacier is doing. Some of the key terms and concepts we're going to talk about. So why study glaciers? Well, you know, they shape landscapes. If you live in the Northeast US, New England, Michigan, Ohio, Pennsylvania, Minnesota, the upper Midwest, you live in a glacial landscape. If you've ever been to Yosemite National Park in California, or Glacier, obviously, National Park in Montana, you know that these landscapes have been set up and shaped by ice. The Pleistocene epoch, basically this is a period from about 1.5 to 2.5 million years before the present. It ended roughly about the end of the last ice age, which is roughly about 10 to 11,000 years ago. And it was defined by glaciation. And if you think about glaciers in the US and Canada, you can see there in the blue where glaciers at one point have covered the landscape, and in Europe. Now, when you think about glaciation, you think about sea level changes. So during ice ages, sea level is a lot lower because that ice I'm sorry, that water is in the form of ice on some land somewhere. So you remove it from the ocean and you put it into the land. So a state like Florida is far, far bigger than, say, current day Florida. Glacial ice today, well, there's obviously glaciers in the US. Most of them, in fact, all of them are what are called alpine or mountain glaciers. These are a function of latitude and altitude. So in Alaska, because it's high latitude, you don't have to go very high up to find one. But if you go to Ecuador or Peru in the Andes, you have to go up to about 15,000 feet in order to find them because latitude is lower. So the lower the latitude, the higher the altitude. The higher the latitude, the lower the altitude. Ice sheets, there are only two. That's it. Only two. Greenland and Iceland. That's it. There are no other ice sheets in the world. And these are strictly a function of latitude. Glacial formation, what happened? So while you don't have to remember the specific numbers here, it's just a sense to give you what happens. How does snow become glacial ice? So fluffy white snow is mostly air. As you begin to melt and compact and expel the air out from the snow, it eventually goes from snow to granular snow to neve to glacial ice, which attains that sort of blue hue to it. So it's the idea of recrystallization taking place. And here's a little graphic. Regardless of what's happening to a glacier, it is always flowing downhill due to gravity, even if it's retreating. So in a glacier, you tend to have two regions, a zone of accumulation where there is more snow each year than you melt during the summer months. And there is a zone of ablation, which is where you lose ice due to evaporation, melting, breaking off, or calving, and sublimation, which is when you go directly from solid to gas. Okay, so now if in order for this particular glacier depicted here to be growing, that fern line needs to be beyond the snout, because that means you would be adding mass to the entire area. But in this case, this glacier in this, as depicted here, is actually shrinking. The movement, you have two basic ideas. You have the idea of plastic deformation, meaning the ice behaves like a silly putty in a way. There is deformation that takes place. And the idea of basal slippage, which is when the ice sort of slips in episodes along the bottom or the rocks below it. And that's the idea of basal slippage or slippage along the bottom. And here's some other, again, glaciers are rivers. They behave just like rivers do, except they do so very slowly. Some of the effects, and again, the idea of abrasion or the idea of movement and picking up of rock as they move along, or plucking, which is basically when you take chunks of rock and you literally pluck them, move them, and then deposit them somewhere else. So continental ice sheets of long ago created things like the Great Lakes and the Finger Lakes of New York. Okay, as the ice moved, it gouged out basically the terrain. And then when the ice melted, it left behind lakes. Or these very specific glacial features that you see, for example, in Yosemite Park. Moraines are basically depositional features. As the ice moves, it pushes dirt and debris forward and then it leaves it behind. It's sort of like when you go to the blackboard and you pushed your finger over the dust in one of those grooves that the little tray has, and then you stop and it leaves behind a little pile, that's it. That's a moraine, basically. And so you get things like eskers, which are like little snake-like mound features. You have these little areas called drumlins, which are elliptical in nature. You have kame and kettles, which are basically little divots where water creates little lakes. Again, the idea of glacial deposition in the US, where glacial deposition and the shaping of the land has taken place. Let's look at, in places like Mount Rainier in Washington, the whole mountain, which is a volcano, is basically covered in ice sheet, not an ice sheet, mountain glaciers. Again, how they move and move forward. Here's some examples where you find them in, for example, the Alps of Europe and in northern Canada. The very distinctive U-shaped valley, notice this is in Switzerland, a very distinctive U. Whereas non-glacial valleys form a V. See it? U for glacial valleys, V for regularly carved by only water valleys. Again, some of the moraines. Notice the color of the water is almost a gray. Notice how the ice becomes cleaner and less gray as you go up towards the top of the mountain. Here's an example. This is in Alberta, Canada. Notice how bright white it is up here and how dirty it is at the end of it. These are the moraines on either side. And to give you a sense of scale, these little dots you see here are cars. So these are really big piles of debris that have been brought forth by the ice. Drift can happen in two ways. It can be unsorted, like a plow, and it can be sorted and stratified because it's carried by water, okay? So here's an example of sorted. Notice how layered it is versus unsorted, which is basically when the plow leaves it behind. All kinds of boulders and rocks that are, mixed in with sand and silt and that kind of stuff. Yosemite, probably the best example. Do you see the letter U? Do you see it? Here's an example of a braided stream. This is in Alaska. Notice how the water has to find its way through all kinds of gravel bars and sandbars. And you can also see the U shape in this valley as well. Here's an example of a glacial erratic. This is a piece of rock that looks completely out of place. And that's the lesson. That's a lesson. Pretty straightforward material. It is easy. The next one's pretty easy too. It's fun. It's interesting. It's something to at least be aware of. So we'll go over the coastal land processes and landforms. So of course the beach, and the beach is but one aspect of it, okay? A coastal zone, it's a high energy and dynamic environment. Even when things are calm and the winds aren't particularly strong and the waves are nice and small. And here's the power of water. An image from 2001 before a hurricane and of course after a hurricane. Again, things that influence the coastal configuration, of course, wave energy, how much sediment there is, and that sediment usually comes from eroded land and mountain material in mountains, the geologic setting, and of course, people. So here's the example. We only see a small percentage of the beach, but there are very specific stages. So the beach is a depositional landform, and it basically responds to whatever available sediment there is. And beaches are made up of whatever material is available. So if you go to Hawaii, you may find some very black and dark volcanic sediment beaches. If you go to a place like Australia or Bermuda, the sand may be pink in color because there's a lot of coral that has been broken up to form the debris that makes up the sand. If you go to some English beaches, some of them may be made up of shingles, very flat sort of pebbles that make up the beach. So whatever it is available, most sand beaches are made up of quartz and feldspar, which is what you see in the background here, sort of little bits of it that have been eroded over time and sorted by size. Again, the idea of the beach, again, a depositional landform. You know, it depends on where you are. There is the back shore, the foreshore, and the offshore region. There's a low tide line and a high tide line. And the beaches will respond in winter because there's more energy in the wave action. A lot of the sand is pushed further in. During summer, the opposite happens. So it really depends on the time of the year, what kind of beach and shore configuration you are likely to see, okay? So that's an example of how how different does a beach look in winter as compared to, say, summer, all right? Wave energy, again, what is the most important agent? Of course, that would be waves, so water. Wave energy is a function of the squared height of the wave. So imagine that you are, you know, even you at whatever age you are, 18, 19, 20, 21, you go to the beach and a 1 foot wave really does nothing to you. Now, same beach, 2 foot wave, no big deal. Now, 2 squared would be 4 feet. A 4 foot wave will push you about a bit. You may be able to brace yourself and withstand it, but a 4 foot wave will do something to you. 4 foot squared would be 16 feet. Now let me know how you would fare in a 16 foot wave. Yeah, not very well. Get it? Wave energy is a function of the height squared. So you go from 1 to 2 to 4 to 16. It makes a huge difference in the amount of energy that's inherent in that system. The idea of waves. So for example, waves are generated by wind. They depend on wind velocity, duration, depth, and this thing called fetch. And so for example, in Delaware Bay, in this image, there's a narrow fetch, so the waves would be smaller, even for the same 45 knot wind, whereas the waves off the coast of New Jersey and Delaware have a much longer fetch, meaning direction over distance over which that wind can blow, creating larger and larger waves. So that's the idea of fetch. The critical depth for a wave is about 1/2 the wave length. So with a tsunami, for example, what happens is there's displacement of water. As you push that up, then the water begins to move in all directions. As it becomes shallower and shallower and shallower, the energy is expressed upward, and you get this very distinctive, destructive power that's taking place. A tsunami wave involves the entire displacement of water, whereas wind waves are simply surface waves, okay? Now, here's an example of a tsunami. What happened in Japan in 2011, and what happened in Indonesia in 2004. Tsunamis are exceptionally destructive and can cause many, many lives to perish because they can move inland quite a bit, especially if the area is especially flat. Here is a video. It is linked on this page. It's also available on the YouTube curated playlist. It's called Beach, a River of Sand. It was made in 1965. And you might think, well, that's old. Why the heck would I want to watch something that ancient? Believe it or not, it is remarkably good still. It explains littoral processes, and it explains coastal processes and the formation of beaches and sand spits very well. It's about 20 minutes long. I highly recommend it because it really goes over everything in the lesson, I think, especially well. So I recommend it. Here's the idea of the longshore current. The waves approach at an angle. Can you see it there at an angle right here, right? And because there's usually a dominant wind direction in every beach, this creates a current that moves in that direction. And they carry with it sediment, they carry with it sand, and in the end goal of longshore current is to generate a straight beach. Okay, so here's the idea of littoral drift, which is beach and longshore beach drift rather. They're carrying material along the longshore current. And you can see this and you can feel this actually. If you go to the beach and don't go very far out, but if you go about 15, 20 feet out where you still feel comfortable and can feel the bottom, and if you decide to bob in the water for a bit, if you wait a few minutes, 10, 15 minutes. Let's say your umbrella was here and you decided to go here. In 15 minutes, you're going to be here. So you're basically going to be moving in the direction of the longshore current if you do nothing, if you just simply wait there. So that's the idea of sediment transport along the beach. Here's the idea of a sand spit. And the idea of transport of material along that beach. And oftentimes you run out of coastline, and therefore the water current slows down and the material is sort of left behind in the form of a sandbar, essentially. Again, the idea of headlands and pocket beaches. And energy is focused on the headlands by wave refraction, which is the bending of waves. And then in the end goal is to deposit here and erode here and to eventually straighten out the coastline. Now, this is a material that's not found in your book, the idea of human intervention in the coastal zone. So there are 4 specific things that humans have basically input into the landscape of coastlines. They're called groins, jetties, seawalls, and breakwaters. So let's go here and look at a place like the Hampton Beach groin field and what they look like, a place like Monmouth Beach, New Jersey. Here's an image from North Carolina. Notice 1, 2, 3, 4, 5, 6. There's a whole bunch of them. And notice how weird the beach looks. It looks very, almost like a sawtooth pattern. And here's a top-down view. Okay. Here's the idea of a jetty. A jetty is 2 side-by-side groins, basically designed to promote travel in and out of the inland waterway. This happens to be Fort Pierce, Florida. Here's another example of a jetty. 1 groin here, another groin here. So combine the 2 form a jetty. And here's the idea of a breakwater. A breakwater is designed to basically help force the waves to break on one end. Notice how much turbulent the water looks here than it does here. So you can basically dock your little boat without any risk of turbulence. And of course, probably the most damaging structure is a seawall. And a seawall can be good and it can be really bad. It can be really bad because it basically can destroy beaches. They protect the inland area, but they destroy beaches. So they're usually built parallel to the beach, designed to protect owners and homes. But again, ultimately, they will destroy your beach. Here's an example of a 1980s. Notice how grainy the image is. This is the town of Seabright in New Jersey. Same image, early 2000s. Notice how they built themselves a beach and they removed the different structures. So this is what happens when you can spend hundreds of millions of dollars dredging sand and making yourself a beach and then letting nature handle it from there on out. So those are the two lessons. I did want to at least cover a little bit on Google Earth and also the Earth Wind map. Here's an image of, for example, sea surface temperatures and currents. So here's an example of, let's look at a current. This is the Gulf Stream. Can you see it? Right? It's moving north. Let's zoom in a little bit closer. And there you have it. You can see the current moving northeast towards Europe. This is bringing warm water into places like the Iberian Peninsula and France and the United Kingdom. Here is a cold water current called the Labrador current headed south and mixing in with the warm water in sort of the central North Atlantic. Now, look at sea surface temperatures. Here's the water of Florida. The temperature is 31 Celsius or 87.8 Fahrenheit. Okay, whereas the water here off the Canadian coast is 41 degrees. So this 41-degree water is mixing in with this very hot 70, 74-degree water off the coast of the Maritimes in Canada, okay? Notice up here, waters in the Arctic Ocean, this is still ice, 28, 28, 28, 28, get it? So it's definitely, you know, something that is distinctively frozen. And if you go ahead and look at the Caribbean and the central areas of the world near the equator, you can definitely see the warm belt of water and the different currents. Notice how chaotic the currents actually can be. So this is a way of looking at the ocean. Notice 88-degree, 87-degree water throughout the world. An inherently dynamic system, as you can clearly see. Anyway, I hope that was useful. I hope if you have any questions, please ask. It's been a great semester and I hope you've enjoyed it. I hope you become a little bit more geographically savvy. If you have any questions, please let me know as soon as you can. Otherwise, I hope you have a fantastic rest of your academic year. Bye.